This video is going to be quite a short one, just recapping everything we've covered about recurrence relations, just going through step by step the process you should be using to solve these. I'm going to use one specific example to guide us here, but it's going to apply to any of the other questions as well. So, first order cases will follow the same strategy, but second order recurrence relations are the more difficult ones. So, that's the example I've taken here. First step is to get all your terms involving UNs onto one side. If you've got a first order equation, you'll do the same, but you're just going to have something like UN plus 1 minus 5UN maybe equals 3n plus 2. So your right hand side is going to be something, everything that doesn't have the UN or UN plus 1 or UN plus 2 involved. The left hand side will be everything involving UN there. You're then going to form the auxiliary equation, and that comes just by replacing your in the second order case, replacing un plus 2 with lambda squared, un plus 1 with lambda, and un just with the constant. So the example we're going from here, gets you here to there. So that's, if you want to do one step before, you can think that what we're really doing there is we're saying we want for now to make the right hand side equal to 0, and we're trying to solve that homogeneous equation. But you can jump straight to the auxiliary equation. You can do this if you want in the first order case, because if you do that in the first order case, the homogeneous equation would be un plus 1 subtract 5un equals 0. But you could make this lambda subtract 5 equals 0, which just would give you lambda equals 5 in this case. But really, in the first order case, this is just a recurrence relation, so you should be able to jump straight to the complementary function anyway. So you can do that, but you don't need to go through that. In the second order case, though, it's difficult because you've got three possibilities. If you get two real distinct roots, lambda 1 and lambda 2, then we can go straight to saying that is some number p times lambda 1 to the n plus some number q times lambda 2 to the n as our complementary function. If we have a repeated root lambda, this is where we might be tempted to try and just say p times lambda to the n plus q times lambda to the n. It doesn't give us enough generality, so we have here in brackets this p plus qn times lambda to the power of n. And if you've got, my complex roots have gone strange there. If you've got complex roots where the argument is the modulus is r and the argument is theta, then you can write it in this form here where you've got r to the n brackets p cos n theta plus q sine n theta. That's the preferable way. If you have the complex roots just in the form of complex numbers, you can write as p times lambda 1 to the n plus q times lambda 2 to the n, but it makes your life a little bit nasty, and because all our terms are going to be real, it's nicer to have this form and get them as real. So in this case, just to re-emphasize that, the moduluses are the arguments theta, so get it into that form, and it's much nicer to deal with. So that's us having solved the homogeneous equation, as in the left-hand side equal to 0 rather than equal to this complicated thing on the right-hand side. The next stage is to pick a child function. That's one thing that solves the specific case of giving us the right-hand side. So you're going to look at the form of the right-hand side. In this case, we've got this function 3n plus 2. This is a linear function, so you'd guess, in this case, your child function would be an plus b. If you had a quadratic on the right-hand side, you'd guess an squared plus bn plus c. If you had a constant, you'd just guess a constant. If you had something like equals 3 to the power n on the right-hand side, or a multiple of 3 to the power n, your child function would be something like a times 3 to the power n. Those are most of the cases that are going to come up. Now, most of the time, they will cover you. But if you remember, there's some cases where it gets complicated. If our child function that we'd guess already appears in our complementary function, so it's possible that we want to go for a times 3 to the n as our child function, but it's already in our complementary function. All you want to do is take what you would go as your child function and multiply it by n, and that should give you a function that will work. The same thing can happen if you're wanting a constant to appear in your child function and the constant appeared in your complementary function. Again, multiply your child function by n, and you should be fine there. You're then going to substitute your child function into the recurrence relation and find the constants a, b, and maybe c that will make that work. So that's going to give you one function that solves the right-hand side. The next step is you're taking your complementary function, you're taking your child functions, and you're just adding them together, and that gives you your general solution. And then if you have initial conditions, that's if you've got u0 equals or u1 equals, you're then going to sub those in to work out what your unknown constants are, and then you've got your particular solution. So just to recap those, when we've got our solution, that's our child function plus our complementary function, that's what we call our general solution. Once we've satisfied our initial conditions, that's what we're calling our particular solution. Thank you very much.